Today we start on important topics related to major theory. Okay. In previous class we also discussed on important topics related to that means this major theory, especially in related to norm LP norm. Okay. So we also discussed this portions in previous class, and obviously this one is that means one of the integral operator. Okay, integral operator of functions is bounded. Okay, bounded by some function. So we also discussed in previous class. Today we also start from product phase. We know about that. First, what is product space? Okay, so product spaces we also discuss today. So we read about that this x and y. Okay, b sets. Then the Cartesian product of x and y defined by then the Cartesian product of this x y denoted with x cross y. Okay, sorry, here we write x and y is defined by all known about this it x Cartesian product y equal to xy belongs to sorry xy. Okay, such that x belongs to x and y belongs to y. Okay, so first element of this, that means pair or this two coordinate system, first coordinate is a belong to x and obviously second coordinate belongs to y. Okay, in this way we also define Cartesian product of x and y. Then what happened? Then this x Cartesian product y are faces. Okay, or b faces, vf space, and we call it product space. Okay, so we also discuss this one, two set related by some Cartesian product and then form one space. Obviously this space is called product space. Okay, obviously some operation is needed here. Okay, but this one will not discuss here. Okay, so next we talked about rectangle. Okay, rectangle, we known about that is subset a Cartesian product b. Okay, of x Cartesian product y is called a rectangle of xy, is called a rectangle of x Cartesian product y. Okay, so now we that means erase that portion and going to further discussion of that. So what happened here are the collection of all rectangles, the collection of all rectangles. Okay, collection of all rectangles of X Cartesian product Y. And here this one, this epsilon, the collection of all finite disjoint union of elements of R. The collection of all finite disjoint union, finite disjoint union of elements of R. Okay. Then what happened? Then we talk about that. Okay. Let X algebra AX. Okay. Let X this algebra AX and Y algebra AY. Okay. Be measurable spaces. Be measurable spaces. Okay. Then epsilon be an algebra. Okay. Epsilon be an algebra. And sigma E equal to the smallest sigma algebra, okay, generated by this epsilon. Okay, the smallest sigma algebra generated by this epsilon. So what happened? This X cross Y, this X Cartesian product Y and this sigma E. Okay, it be measurable spaces. Okay, be measurable spaces, and here then what happened? Then X Cartesian product Y and this sigma, okay, be a product measure space. Okay, be a product measure space. Okay, now sigma E equal to what? Okay, sigma E equal to X AX Cartesian product AY. Where is that portion? Sigma E equal to AX Cartesian product AY. Okay, then X Cartesian product Y and AX Cartesian product AY. B product measure space. B a product measure space. Okay. Then what happened? We also talk about section of sets. Okay. We erase that portion and going to further discussion of that. Section of sets. Okay. Section of sets. Here let XY be sets. let x y be sets, okay, and E be a subset of, and E be a subset of x Cartesian product y. E subset of x Cartesian product y. Okay, so for x belongs to this x and x section of E, okay, be a subset of y denoted and defined by here ex equal to y belongs to this y and xy belongs to this e. Okay, let x y be sets and E be a subset of x Cartesian product y and E subset of x Cartesian product y. Then for x belongs to x section of E be a subset of y denoted and defined by ex equal to y belongs to this y and xy belongs to E. Okay, so next we talk about y section of E. Okay, we erase that portion and this one are similar, so we write it here same thing, just we change something here. For y belongs to y, okay, here y section of E be a subset of x, okay, be a subset of x denoted by ey equal to x belongs to x, okay, such that xy belongs to E. Okay, then this one is the y section of E, be a subset of x and denoted and defined by this one. Okay, since next we talk about some proposition, we erase that portion and going to discussion of some proposition. Okay, x section of E and y section of E we also discuss today. Okay, y section of E be a subset of x and x section of E be a subset of y. Okay, then ex equal to y belongs to y such that this, that means pair x pair coordinates xy belongs to E and y section of E equal to x belongs to x and then x, this pair coordinate xy belongs to E. Okay, now we're going to discussion of some proposition. We erase that portion and going to discussion of some proposition. Okay, so we write it now. Let x this algebra and y be a measurable space and y is be a measurable measurable spaces. Okay, and let E be a and let E be a. Okay, be a cross B measurable sets. Then what happened? Then here first one Ex equal to Exb B measurable and for all x belongs to x. Okay, and 2 E y b a measurable for all y belongs to y. Okay, then what we talk about that, talk about section of function. Okay, now we're going to discussion of x section of some set E and y section of some set E. Now we're going to discussion of some section of function. Okay, we write it now. Section of function. Let x and y be non-empty set and if x Cartesian product y to this k be a function. Okay, be a function, and for x belongs to x, for x belongs to x. Okay, for x belongs to x section of f, x section of f. Okay, is a function, is a function if y to k, if y to k defined by, okay, defined by here fx equal to f of y. Okay, capital F x y. This one belongs for all y belongs to y, and this one obviously belongs to k, some field. Okay, so what happened here, if x equal to, that means some function x section of f is a function if y to k defined by f of y, if x equal to f of y. Okay, and now we erase that portion and going to discussion of another section of function. Okay, here we write about it. For y belongs to y section of f, y section of f is a function g, is a function g x to k such that fy equal to, okay, gx equal to f of xy, for all x belongs to this x and this one belongs to k. Okay, then this one is the y section of f. Y section of f means some function of x, and x section of f means some function of y. Okay, now we talk about some example here. Okay, we write some example. First, f of xy equal to x square plus y square, and x section equal to, okay, x section of f, x section of f equal to f of y equal to, here f of xy equal to, here x square plus y square. Now two section of f equal to, okay, here f of y equal to 4 plus y square. Okay, now we're going to further discussion of that. We erase that portion and going to discussion about that. We write again some proposition. Okay, we erase that portion. Write some proposition. Okay, let x this algebra and y this b be measurable spaces, be measurable spaces, and let if x Cartesian product y, and let if x Cartesian product y to k be a Cartesian product b measurable function, measurable function. Okay, then what happened? Then first one, if x be measurable function, be measurable function for all x belongs to this x. Okay, and number two, here fy be a measurable function, a measurable function for all y belongs to y. Okay, then that means what we get here, we get that means those measurable x section of this function and y section of this function. Okay, we write it now. This one are p measurable functions and a measurable function. Okay, and similarly we also talk about that this section of some set are b measurable and a measurable. Okay, so now we going to discussion about one important proposition. Okay, so we write it now. One important proposition. We erase that portion and going to write it some important proposition. Let X this algebra mu be a measure space. Be a measure space. Okay. Let if x to 0 plus infinity be a measurable function. Be a measurable function. Okay, and define a set function comma and define a set function. Define a set function comma here a to 0 plus infinity by this comma e equal to this comma equal to integration of e f t mu. Okay, for all e belongs to this algebra e. Okay, marked as 1. Then comma b measure on. Then comma b measure on x this 50. Okay, and obviously we talk about another one. Okay, if mu and comma are two measure on a measurable space xa, if mu and comma are two measures okay on a measurable space okay, this x this script a, then we will discuss for existence and uniqueness of a measurable function if for which okay we also if command mu are measure space or measure that is two measures on a measurable space x the script a. Okay, then we will also okay discuss for existence and uniqueness of a measurable function. Uniqueness of a measurable function if here x to 0 plus infinity. Okay, for which one hold, for which one hold. Okay, so we also discuss this important theorem. It is that portion, and going to discussion one important theorem. This one is Radon Nykodym theorem. Okay, we just read the statement of Radon Nykodym theorem. Now, statement of Radon Nykodym theorem. Okay, let mu and gamma be sigma finite measures on a measurable space this x50. Okay, such that this gamma less than absolutely continuous with respect to mu. Then what happened? Then there exists a measurable okay function if there exists a measurable function if here, okay, x to 0 plus infinity such that gamma e equal to integration of e f d mu. Okay, for all e belongs to this algebra. Okay, marked as 1. Then the function f is unique. Okay, in the sense that okay, if gx to 0 in plus infinity, okay, be another measurable function, okay, such that this one hold. Okay, then g equal to f mu almost everywhere, okay, on x. So what happened is here, let mu and gamma be two sigma finite measures on a measurable space x, this algebra script A, such that gamma is absolutely continuous with respect to mu. Then what happened? Then that means we see that here, then there exists a measurable function if x to closed 0 plus infinity such that here gamma e equal to integration of e f d mu. Okay, for all e belongs to this algebra. Then the function f is unique in the sense that if g be another function, measurable function such that one holds, then g equal to f mu almost everywhere on x. Okay, this one is the important Radon-Nykodym theorem. So today I'll stop here. Okay, if you get this type of video, please subscribe my channel. If you gives like, then please raise the like options, and if you have any questions, comments, suggestions, please write it in comment box. So please subscribe my channel. Today I stop here.